Hello, everyone. Thank you for joining us today. I'm glad to be able to welcome you to another Authority Partners webinar. My name is Admir, and I'm a principal software engineer at Authority Partners. And in this session, we will be talking about Azure AI Search, or more specifically, how we can use Azure AI Search in the context of RAG and AI agents. There is a lot to cover, a lot to go through. I will try to speed up through some of the topics, but just a heads up that this will take a little bit longer than our usual 1 hour session. Most of our talk today will be related to RAG, or retrieval augmented generation, in some way. So I would like to start from there, just to provide some context, essentially, for those who might not be familiar, and just to set some foundation for the rest of the talk. Even though I believe many of you are already familiar, at least with the term RAG. So RAG stands for retrieval augmented generation, and it's a pattern for grounding model outputs in external data. That's kind of a very simple definition. It's based on the principle of in-context learning, which is basically the ability of language models to reason over information provided to them at runtime or as part of the prompt, right? So you take a language model, you give it some instructions, you kind of take user question, user query, you concatenate some additional information that might be relevant to the user query. You send all of that to the model as a prompt, right? And the model generates an answer that is grounded in the information that you have provided. And that is basically RAG. So it's relatively simple and straightforward at a high level, right? But it actually addresses some of the inherent limitations of language models, primarily lack of access to the private data, as I already mentioned, but also lack of access to the current data, such as like data that was updated or created after the model was trained. However, for all of this to work reliably, we have to be able to retrieve the right information at the right time, basically when the user asks for it. And that kind of makes retrieval quality critical, and that is where vector search then comes in. Vector search is another term. I believe many of you heard about it. It's also often kind of mentioned together with AI agents, RAG, and so on. So vector search is a search technique that allows us to match content based on semantic meaning or semantic similarity rather than exact keyword matching compared to a traditional text or keyword search, right? So it's more robust to phrasing differences, misspellings, and so on. So when you take in context learning on one side, which allows language model to reason over information provided to them at runtime, together with semantic retrieval or vector search, which kind of helps you find the right information in the first place, you get what is known as RAG, or retrieval augmented generation. Now, the diagram that you see on the slide illustrates a typical RAG implementation. And as you can see at the high level, RAG consists of two main parts. That's the data ingestion pipeline and the data retrieval pipeline. Data ingestion pipeline is responsible for ingesting, processing, and indexing content, or preparing content for efficient retrieval later on. That's its primary purpose. And data retrieval pipeline, as the name implies, is responsible for retrieving and processing content when responding to user queries, essentially. RAG pattern, like almost everything you see on this diagram, can be implemented almost entirely within Azure AI Search. Almost all of these blocks that you see on the diagram are in some way covered in Azure AI Search, from data ingestion pipeline to data retrieval pipeline, and even some additional features and capabilities that are purpose-built for RAG scenarios and AI agent grounding. And that is basically what we will be talking about today. So let's start from the very beginning of this diagram, from the top, actually, and that is the data ingestion pipeline. So data ingestion pipeline is where raw data becomes retrievable knowledge, we could say it that way. You know that in the context of RAG, we are typically working with unstructured data, documents of all kinds of formats. And this is the stage where we take those documents and transform them into something a retrieval system can actually work with, right? And with vector search at the core of a RAG stack, our data ingestion pipeline must actually prepare content for the vector search, for semantic retrieval later on. And that actually involves a couple of steps. First, we have to ingest content from the data source, right? For example, documents from the blob storage. Then we need to extract content, parse documents and extract content. Then we need to split that content into smaller pieces or chunks that are suitable for semantic retrieval. Then we typically enrich those chunks with some additional metadata, for example, page number, maybe document title, section title, and so on. And then finally, we need to generate embeddings or numerical representation of that content, vectors essentially. And then as a last step, we push that content in that form into our search index or into our knowledge base, right? This is one of the areas, we could say that way, where Azure AI Search can actually do a lot of heavy lifting for us. So instead of building and maintaining a custom data ingestion pipeline, we can simply kind of delegate that to Azure AI Search, which, as I already mentioned, provides built-in capabilities and primitives for almost each step of this data pipeline that we've seen earlier. So let's see how this looks like in Azure AI Search. So at the core or at the center of Azure AI Search is the search index. Just some foundations basically to better understand what we will be talking about later on. So at the core of Azure AI Search is the search index. Search index is where our searchable content is stored in the end. Index is defined by a schema which describes fields and their attributes, whether the field is vector field, text field, whether it's searchable, filterable, and so on. So it ultimately defines the shape of our data or the shape of our retrievable knowledge, right? Next, we have the data source. Data source tells Azure AI Search where to pull content from. For example, it can be, for example, blob storage, SQL database, Cosmos database, and so on. In our examples, we will be using blob storage because we are kind of ingesting documents. So data source is the entry point into the data pipeline. It provides raw data, which is then processed before it gets pushed, processed and shaped, right, before it gets pushed into the index. And in the middle, we have indexer. And this is where things start to get a little bit more interesting and concrete when speaking from the perspective of the data ingestion pipeline, because indexer is actually the orchestration engine of the data ingestion pipeline in Azure AI Search. It connects data source on one side to the index on the other. And in fact, in Azure AI Search, indexer acts as a crawler. It runs automatically on a schedule, right? It can automatically pull data from the data source. It extracts the content from the documents, for example, processes the content, and then pushes content into the search index. It controls the scheduling, like when and how often to run. And what is interesting, it also provides built-in change tracking, which means that each subsequent run will process only modified content, like modified documents. It also defines how that content or data will be processed. However, the actual logic, actual processing logic, right, is defined in what we call a skill set. Skill set is another object in Azure AI Search. It's always attached to an indexer, right? But you can attach one skill set to multiple indexers, essentially. You can think of a skill set as a recipe that kind of tells Azure AI Search how each document, how content actually should be processed. Skill set contains one or more skills, and skills are nothing else but individual processing steps of that recipe, technically speaking, right? So, for example, in our example, what we have text split skill, for example, for chunking. I mentioned earlier that we need to split content into multiple pieces or chunks, right, that are suitable for semantic retrieval. We do that with the text split skill. Embedding skill is responsible for embedding generation and so on. This is also known as integrated vectorization in Azure AI Search. So if you ever kind of end up reading some documentation or articles and you kind of find this term, it's basically a term, integrated vectorization. It's just a term that is used to say that these vector search capabilities are kind of built in and supported natively through built-in skills, so that we don't have to implement it like as a custom pre-processing step in our own application, right? So because Azure AI Search kind of already supports this out of the box. Okay, so rather than keeping this at the diagram level, I will switch now to Azure Portal. Just for a quick walkthrough, it's not going to be like a step-by-step demo. I just want to show you how this actually looks like in Azure. So just give me a moment to switch my screen share to Azure window. Okay, we're here. I hope you can see it. So we already mentioned a couple of building blocks or a couple of concepts and building blocks of data ingestion pipeline, like starting from the data source, right? But there's really not much to talk about data source. It's, as I mentioned, it's simply a reference to the underlying storage system. In our case, we are using blob storage. So not much to talk about here. So we can move on to the next kind of building block, which is indexer. Indexer, as we mentioned earlier, is basically it kind of manages the whole execution, right? It controls scheduling, it handles change tracking, and so on. As you can see here, you can also view like previous runs. You can check the run status, run history, and so on. Again, I mentioned this is already kind of everything is already prepared. So you can see a couple of runs that executed before. You can also see some, if you open some specific run, you can see errors or warnings or anything like that. And in fact, if you have any error or warning, you can also use so-called debug sessions in Azure AI Search, which allows you to actually run the indexing pipeline on a sample document that you select, and then you can inspect the whole pipeline at each step of the process. So it's a pretty neat feature for debugging, and especially if you have more complex data ingestion pipelines running inside Azure AI Search, right? Okay, so we said that indexer manages the execution, right? But the actual processing logic is defined in the skill set, right? So, and what you see here right now on the screen is an example of a skill set that is set up to prepare content for semantic retrieval. As you can see here, everything is kind of declarative, right? So you can think of a skill set as a declarative enrichment graph, so when the Azure AI Search processes a document, it creates a so-called shared enriched document, which acts as a shared working context for the whole indexing pipeline. And then each of these skills, as you can see them here, each of these skills actually works on the same shared working context, uses the same shared enriched document, applies its own processing logic, and then saves the result back into the same shared enriched document. And then at the end of the pipeline, that final enriched document then gets pushed into the search index using these index projections and field mappings, essentially. So again, as you can see, everything here is declarative. There is no, it's just a JSON object, as you can see. So there is no any procedural logic because we are only using built-in skills. So all we need to do is simply configure already built-in skills that are already built into Azure AI Search. There is obviously a possibility to use your own, to write actually some custom logic. If you want to write custom skills, that's also possible, but it's kind of out of scope of our talk today. It's just good to mention that that's also possible. But technically, using only built-in skills, you don't have to write that code. All you need to do is just to configure existing built-in skills. As you can see, like each of these skills, we have text split skill here, and the next one is the embedding skill. Each skill defines its own properties that we need to configure. Like embedding skill, split skill defines the chunk length, the overlap length, and so on. Embedding skill defines the model, the dimensions, and so on. Each skill also defines inputs, outputs, and so on. So each skill kind of builds on the outputs, given that they all work on the same shared working context, right? Each skill kind of builds on the outputs of the previous skills, progressively enriching and processing the document. Okay, so I intentionally skipped the first one, the first skill in the earlier description. This is actually our content extraction skill. If you remember, I mean, the first thing that we need to do after ingesting the document, that is what Indexer does automatically for us, right? Pulls the document automatically from the blob storage in our case. But then the next step is to extract content from that document. Now, content extraction in Azure AI Search is actually natively supported. It's built into the indexing pipeline. So even when we don't have explicit content extraction skill like here, some content extraction is done implicitly. However, that default content extraction might not always be enough, because documents can be, can actually be more complex. So the default content extraction might not provide the quality needed for effective retrieval later on. For example, documents may documents often carry meaning through their structure, right? For example, their layout, their headers, footnotes, tables, images, diagrams with arrows and labels, and so on. So sometimes the information is encoded in how the information is presented, not just in the words themselves, right? I will show that in a minute, what we mean by that. And in these situations, to mitigate these challenges, this actually makes content extraction potentially the most challenging step of the data ingestion pipeline. Obviously, it depends on the type of data, on our own use case, what we need to support, and so on. But it can potentially be the most challenging step of the data ingestion pipeline. And to kind of address those challenges, we typically use, instead of using a simple parsers, right, extracting textual content from documents, we typically use AI models and run documents through these AI models to extract and understand content. And in Azure AI Search, we also have, let's call them specialized content extraction skills, like the one we are using here. As you can see here, we are using document intelligence layout skill. Another example is Azure AI content understanding skill. These skills use behind the scenes, under the hood, they use other Azure AI services, such as document intelligence, for example, in our case, to perform a more intelligent and structure-aware content extraction. This is known as AI enrichment in Azure AI Search, and content extraction, like application of AI models during indexing in order to transform and enrich content, right? That's what we call AI enrichment. And content extraction is just one type of AI enrichment. And Azure AI Search actually provides many additional AI enrichment skills, such as OCR, anti-recognition, key phrase extraction, PII detection, and many more, as you can see on the screen. Okay, so just to show you what we mean by, the documents can sometimes be more complex. It's not, I mean, this document is not generally complex, but it's complex enough to showcase this example. So what I have here is a document that contains cost information presented in a table. However, this table is not a real table. It's actually an image. And the text is not obviously the real text. It's just text on the image, right? Now, if I try searching for this information, if I try to retrieve it, as I mentioned earlier, this is already indexed, right? This document is already I already prepared this demo earlier, so we are not going through every single step, but this is already indexed. And if I try searching for this information, I'm going to use natural language query, but we still don't have any agents, right? Just a reminder, we are simply testing our retrieval. So if I try searching for this information, and if I kind of go, it should be at the top result, probably this one. And if we scroll to the right, you can actually see that it actually extracted this information from that image. So you can see these pricing information, right? We have some additional HTML tags because it actually rebuilt the table, right? But you can see the actual content. You can see that it actually extracted the information. So the document layout skill, which we use for content extraction, was able first to extract content from the document, to extract images from the document, and then to extract content from that image, right? And also it was able to understand that content to kind of rebuild it as a structured markdown table. In our case, it used HTML text to represent table, but it was able to preserve this structure, which is also important because later on, when we pass this as a context to language model, that structure might help agent answer correctly if we ask some specific question rather than simply extracting and presenting it as a flat text, right? So that is example, like when I mentioned earlier that some of these, that sometimes information is encoded, encoded in how the information, sometimes the meaning is encoded in how the information is presented, right? In this case, we never actually explicitly say that the cost of the paycheck for employee +2 or more is 89. It's just implied based on the layout of this table. And preserving this structure is important, and you will see it at the end of today's session, that it helps the agent kind of actually answer the related questions. Okay, I'm going to switch now back to the presentation. So let's say that we now have our data ingestion pipeline set up, right? And I hope you can see the screen. Sorry, it took me a moment. So let's say that we have our data ingestion pipeline set up, right? So the next step is the data retrieval, right? And I mean, that's the whole point. The real value comes when we can actually retrieve the right information at query time. So that's our next topic, data retrieval pipeline. The most common practice in RAG applications is to implement retrieval using vector search. This is probably already known to many of you that are listening today. So vector search, as already mentioned before, transforms content into numerical representations that carry the semantic meaning of that content. We have some illustration on the slide. I hope it helps you visualize what the vector search does. So we kind of convert content, any form of content, text, video, audio, images, into numerical representations that we call vectors or embeddings, and that carry semantic meaning of that content. And that allows us then to match content based on semantic similarity. Then, for example, when the user asks a question, we can actually retrieve or find contextually relevant pieces of our content, chunks that are kind of relevant to that user question, even if they don't share the exact same keyword. And that's actually the main value proposition of the vector search. Now, the vector search, like the diagram here on the slide, illustrates the most typical implementation of the retrieval pipeline using vector search. It's quite basic, but as you can see, when the user query comes in, it may first go to a so-called query rewriting step, right? Query rewriting, it's optional, but we typically do it. And the goal of query rewriting is to capture conversational context. You know that RAG applications are typically chat-driven, conversational, right? Chat-driven. So there is a lot of conversational context that might not be contained in the latest user query, right? So query rewriting step actually tries to capture that conversational context or to convert that conversational prompt into a single complete search query that fully captures the user intent. I hope that's clear. Then once we have the rewritten query, the next step is to generate embedding for that rewritten query using the exact same embedding model that we use during indexing, and then we use that embedding or vector to perform vector search. Now, in Azure AI Search, like when we perform the vector search, Azure AI Search actually performs so-called k-nearest neighbor search in order to retrieve top k most similar vectors. That's how we kind of measure the similarity. In other words, we are actually retrieving top k most relevant chunks. Now, when it comes to ranking in vector search is primarily determined by the chosen similarity metric. On the previous slide, we had like cosine similarity mentioned. So the ranking is primarily determined by the chosen similarity metric, such as cosine similarity, but Azure AI Search also supports some other metrics, such as for example, Euclidean distance, dot product, and so on. One interesting thing that is worth mentioning is that embedding step or embedding generation is typically implemented in our application as a pre-processing step, right? Even before we call whatever search system we are using, for example, let's say some vector database, we typically generate embedding manually in our application. Now, with Azure AI Search, we can also use integrated vectorization here. So we don't have to do that manually. We can simply issue a textual query to Azure AI Search, and then Azure AI Search handles embedding and vectorization for us before kind of executing the vector search. One thing that is kind of worth mentioning is that early in the AI wave, vector search was seen as a definitive solution for retrieval. However, it didn't take us long to realize that vector search alone might not always be sufficient, for many real-world retrieval scenarios. And then, as the systems matured, the retrieval stack also evolved, and similarly, Azure AI Search as well. So today, it kind of incorporates and offers additional retrieval techniques that complement and build on top of vector search with one goal, and that is improving retrieval quality. And the first such technique that we are going to talk about is good old text search. You might have already figured out that Azure AI Search is not like a typical vector database. It's actually like a search engine, right? So text search is like a first-class citizen here. In fact, we don't even need to do anything special to enable text search. All we need to do is to define a searchable text field on our index, and that field automatically participates in the text search. From the technical perspective, as the slide illustrates, text search works by applying language-specific text analysis in order to break down textual content into individual terms, right? And then it builds, from those individual terms, it builds so-called inverted index, which is nothing else but a mapping between those individual terms to the documents in which they appear, right? And then at query time, it uses BM25 scoring algorithm for ranking. So it's kind of pretty standard stuff for text search. And you might be wondering why do we even need text search, right? Because we mentioned earlier that vector search is more robust, especially phrasing differences, misspellings, and so on. So why are we going back kind of to text search? And in many cases, vector search is going to be better. However, there are still some cases, some scenarios where text search can actually be quite effective. And that is primarily when exact term matching is required. I have an example here on the slide. Let's say that we have just, so you understand the use case a little bit better. Let's say that we have an AI agent or an assistant, right, for machine maintenance. So it can answer various questions about machine maintenance, right? Different machines, parts, and so on. So querying that agent or that assistant for some specific machine model, part number, might be actually better served by text search, like keyword search, rather than vector search. Especially if the knowledge base is very large with many, let's say, with many machine models with similar names, with similar kind of documentation indexed across different machine models, where the differences are mostly in these exact values, right? When we ask to get information about, this is just some arbitrary, code word or product name. When we ask, let's say, for information about XR45, we don't want information about XR55. Right? We want exactly this and only this, right? We don't want to, accidentally get like a wrong answer. I hope it's clear. So text search can actually still be valuable, right, and beneficial. And as I mentioned, it's mostly when exact term matching is required, like when we have some of these like product names, code words, when we are searching for some identifiers and so on. So technically, we are now saying that both vector search and text search are kind of can be used depending on the scenario. However, how do we now know which one is good for us? Obviously, when we know the exact use case, when we know the data, we can make some predictions, right? We can predict what types of questions the users will be asking. We know what types of queries we need to support and so on, depending on our use case. But still, user queries can take many different forms, from very vague conversational queries to highly specific and precise keyword-driven searches, right? Which is why relying on a single retrieval method is often, not sufficient, and which is also a reason why today we often actually combine these two retrieval methods, which brings us to the next topic, next retrieval technique, and that is hybrid search, actually. Now, as the name implies, hybrid search combines both vector search and text search. Just to summarize, they provide these complementary retrieval capabilities, right? Because they approach it from different perspectives. On one side, we have vector search, which excels at matching content based on semantic similarity, semantic meaning. So it's much more robust to and less sensitive to phrasing differences, misspellings, and so on. And on the other side, we have text search, which excels at matching important words that might be diluted in an embedding, right? Now, from the technical perspective, hybrid search works as a single search request, single search query with both vector and text search parameters, obviously. Under the hood, Azure AI Search executes both vector search and text search independently, produces two independent result sets, each ranked using their own respective ranking mechanism, right? But then it fuses or merges, right, both of them together to produce a single unified ranked list using so-called reciprocal rank fusion algorithm, which just at a high level, I won't go into details, at the high level, reciprocal rank fusion favors those results that rank high across both retrieval methods. Benchmarks actually show that hybrid search actually outperforms both vector-only or keyword-only search on average. Obviously, it depends on the use case, but on average, hybrid search outperforms both of these as individual kind of retrieval methods. I would always advise you to run your own evaluations, right? To run your own kind of tests and see what works best on your own use case. But these public benchmarks can actually serve as a good baseline on where to start from. Okay, so after hybrid search, the next step in the retrieval pipeline or the next retrieval technique that we will be talking about is re-ranking. In Azure AI Search, it's called semantic re-ranker or semantic ranker. The role of re-ranker is actually to reorder results returned in the previous retrieval steps, such as, for example, hybrid search, based on result semantic relevance to the query, right? So it doesn't retrieve new results. It doesn't, it simply refines the ordering of the existing candidates, which typically leads to improved retrieval metrics, ranking metrics, and it also reduces the amount of irrelevant or low quality context passed to LLM, which is still important today. Like even with today's large context windows available in language models, precise retrieval still matters because sending excessive or loosely relevant context to LLM can have negative consequences. First, it can increase latency and cost because of all those additional tokens that we're sending, right? And it can also degrade answer quality because of all that additional noise surrounding potentially relevant content, right? So ideally, we want to pass small, focused, high-quality results set as a grounding context to LLM. Typically, let's say top 5, top 10 results. I mean, obviously, it depends on the, there's no rule, right? It depends on the data and use case, but we most probably don't want to pass top 100 results, right? Now, from the technical perspective, semantic ranker in Azure AI Search uses a so-called cross-encoder model. This is important information. I'll explain it in a minute. Uses cross-encoder model to re-rank top 50 results returned from the previous retrieval step, such as, for example, hybrid search. And then it rescores them on a scale from 0 to 4, where higher number indicates stronger semantic relevance to the query. Now, if you've been closely following, you might have noticed that I mentioned, that re-ranker reorders results based on the semantic relevance to the query. So you might be wondering again, why are we, again introducing another semantic kind of relevance check or comparison? Because isn't that what vector search is already doing? And the answer lies in the way that semantic relevance or semantic similarity is actually determined or calculated, right? With cross-encoder, I mentioned that we use cross-encoder model. It's a type of AI model. So cross-encoders are much better than embedding models, which are B-encoders, by the way, at this deep semantic understanding, because they can actually process, I try to illustrate that here with this slide, because they can actually process two inputs at the same time, two texts, right? Compared to embedding models, which only accept one single input, they produce embedding, and then we compare it on the level of embeddings, right? So cross-encoder actually accepts two inputs and can process two texts together. For example, user query and a candidate document, candidate result, which allows it to kind of capture more nuanced interactions, more like similarities, differences, and so on. It's kind of ideal for re-ranking. However, the negative is that it's much slower. It's much more computationally expensive, which is why retrieval is typically split in two stages. We have fast initial retrieval and then followed by slower but more precise re-ranking on a smaller candidate set. Benchmarks actually show that combining hybrid search with semantic ranking delivers significant improvements in terms of retrieval quality, like ranking metrics, even going up to 22 points on the NDCG top 3 metric, which is quite something, right? It's quite significant. Benchmarks are run across different data sets, different languages, and so on. These are actually Microsoft public benchmarks. You can find them online as well. Okay, so the next one thing that I forgot to mention, sorry, is that semantic re-ranking is not free, unfortunately. It doesn't come, it's not bundled with the general Azure AI Search pricing, but it's optional. So if you need it, you will need to pay for it. Right? The next retrieval technique that we're going to talk about is called query rewriting. This is the last one in our retrieval pipeline. So far, we have been talking about like how to let's say retrieve and rank results, right? And query rewriting actually focuses on how to improve query itself. So it's a pre-retrieval step. It runs before semantic ranking. It runs before hybrid search. It actually expands or transforms the original initial search query into up to 10 semantically related variants, right? It actually creates alternative expressions of our original query, which can potentially help surface some additional documents that might have been missed using the original wording, right? And now I have to mention that vector search is already quite robust to these different phrasing differences, right? So if you are using vector search already, query rewriting might not provide the same level of improvement as we expect, for example, from a re-ranking step. However, if you're already using re-ranking, query rewriting is completely free, so it's kind of worth exploring or at least evaluating, on our own use case, whether we have any benefit, even if marginal. The only thing that we need to take into account is that all these additional alternative queries, they all need to be executed, right? So they actually consume the compute resources of our Azure AI service. So it's something to take into account when kind of calculating and determining the trade of whether it's worth, I don't know, whatever is the increase in the retrieval quality, right? Okay, so far we have kind of covered all these individual metrics, retrieval techniques, and here is how they come together. This is just a quick summary, just to see how everything fits together in the end. We can say that Azure AI Search retrieval stack is split into two stages: L1, which we call re-equal, and L2, which we call re-ranking. When the user query comes in, it may first go through query rewriting step, which we just explained, right? It transforms or expands the query into multiple additional, like semantically related query variants, and then all those queries are sent together into L1 when they are executed in parallel. The L1 is responsible for quickly scanning the index, right, to identify initial set of candidates using either text search, vector search, or as a recommended hybrid search, which we have illustrated here. Now, whenever we have parallel queries running as part of the same search request in Azure AI Search, it could be either hybrid search, which runs both text search and vector search in parallel, or it can simply be multiple vector queries running in parallel. That is also possible. We can even assign different weights to vector queries and so on. So whenever we have multiple queries running in parallel as part of a single of the same search request, Azure AI Search will actually execute all of those subqueries individually. It produces individual, like a separate result sets, each ranked using their own ranking methodology. But then in the end, they're all kind of fused or merged together using reciprocal rank fusion. Now, depending on if you are using re-ranking or not, this may be the last step for us, right? If we are not using re-ranking, this will be the result that is returned by Azure AI Search to us. If we are using re-ranking, then this is the result after the reciprocal rank fusion is passed into the L2 stage for re-ranking, which again re-ranks, reorders the top 50 results returned from this previous step. And the main goal again of this re-ranking is to actually surface or push the most important, most relevant chunks to the top, which should potentially allow us to pass smaller and smaller context to LLM, right? So if we are passing top 10 results to LLM, there is a difference whether the chunk appears at 11 position or 10 position. Difference is whether the LLM is going to see it or not, basically. So even pushing a couple of places up, can make a difference. Okay, it's also worth mentioning, as you can see here on the diagram, we didn't mention that earlier, but it's worth saying that vector search itself also implements a similar two-step process, but it's only used, it only applies when we use so-called vector optimization, storage optimization techniques. And that actually brings us to our next topic, and that is vector storage optimization. This should be a quick one, but it's quite interesting and important. We already talked about vector search, right? We already kind of covered what it is. So vectors or embeddings are numerical representations of the content, right? They carry semantic meaning of that content. They allow us to compare content, for semantic, based on semantic similarity and so on. But they can be actually quite large. We often say they are high dimensional, right? Which makes searching over vectors and working with vectors potentially expensive in terms of compute, in terms of memory requirements, and so on. However, and that is basically then to make vector search practical at scale, modern search systems then rely on different optimization techniques. And Azure AI Search also supports some of these capabilities. But before we actually talk about those, it helps to better understand these memory and storage requirements and why these optimization techniques even matter, right? So it helps to understand the structure of a vector and its raw storage footprint. So as you can see on the slide, we already said it, vectors are numerical representations of content, but literally speaking, they are an array of numbers produced by an embedding model. The length of that array, or the number of elements in an array, represents dimensionality of the embedding. For example, 1,536 dimensions or 3,072 dimensions. These are some common values we use today. In Azure AI Search, vector fields actually can be stored using different data types, from standard 32-bit floats to highly compressed formats like binary vectors, where each dimension is actually stored as is represented as a single bit, either 0 or 1. But most commonly, embeddings are stored as 32-bit floats, which means that each dimension actually takes 4 bytes. The raw storage footprint of the vectors is then determined by the 3 things, right, of the vector index. First, number of vectors, total number of vectors, obviously, then the number of dimensions per vector, and then also the size or bytes per dimension, which is determined by the data type size. So if we assume that we are using 32-bit floats to represent our vectors, a single vector with 3072 dimensions, which is not uncommon today to use, by the way. That's why I kind of used it as an example. So a single vector with 3072 dimensions stored as 32-bit float requires about 12 kilobytes of space. And then when you multiply that by tens of thousands or hundreds of thousands of vectors, which is not really that hard to reach, it kind of quickly adds up. And the example we have here is that at 1 million vectors, that basically becomes about 12 gigabytes of raw vectors before actually indexing overhead. Sorry. Okay. Now, the main concern, like why this matters, this storage kind of footprint, the main concern actually comes from a fact that vector index is memory bound. So when we use HNSV, which is basically the algorithm that we use for approximate nearest neighbor search, the vector index must be loaded in memory in order to support efficient retrieval or support fast traversal, graph traversal during queries, because it involves a lot of random access. So technically, memory becomes the main bottleneck, right? And that is why vector index optimization techniques like compression, quantization, dimensionality reduction, truncation, they are critical to making vector search scalable and cost-effective. Now, Azure AI Search supports two optimization techniques. The first one that we are covering is quantization or vector compression. So quantization is a vector compression technique that reduces both the memory and storage footprint of embeddings by converting native 32-bit float, for example, produced by an embedding model, into a narrower or smaller data types, such as, for example, integers or binary, right? So scalar quantization compresses embeddings or vectors by representing each component, each number of the vector, right, as 8-bit integer instead of 32-bit floats. So we have 8 bits instead of 32 bits or 1 byte instead of 4 bytes per dimension, which is about 75% reduction in size. Binary quantization is similar, but it compresses embeddings by representing each component as a single bit, either 0 or 1, which is even more drastic, right? And the scalar quantization, it kind of goes up to 96% reduction in the vector index size. Another technique is called vector truncation. So if the embedding model supports so-called matryoshka representation learning, we can actually reduce the vector size by truncating dimensions, or simply put, we can store only the first n dimensions of the embedding and then just drop or remove the remaining part. Matryoshka representation learning makes this kind of safe because the model is trained to produce embeddings where early dimensions actually carry the most important semantic information, which means that we can then cut off, some part and then still keep the most important information. Now, obviously, both of these optimization techniques result in some information loss, as I just mentioned, even quantization, truncation as well. So it's all fun and games until the relevance drops, right? Because reducing vector precision through quantization and truncation, can actually significantly impact our retrieval quality. However, that is where oversampling in Azure AI Search, oversampling and rescoring come in. That's the two-step process that I mentioned earlier, two-stage process inside the vector search. So when we use these optimization techniques, our main vector index is compressed. That is the vector index that is loaded in memory. However, we can still keep full precision vectors stored on the disk. So with oversampling, Azure AI Search first retrieves a larger candidate set from the compressed vector index than what the query requested. So for example, if the query requests top 10 results, Azure AI Search may retrieve top 50, depending obviously on our oversampling factor. It can be anything, top 50, top 100, right? But the point is that we are retrieving more results than what the query asked for. And then in the second step, we rescore those top 50 results using full precision vectors that are still stored on the disk, right? Non-compressed vectors, in order to mitigate some of this information loss, which is introduced by compression, truncation, and so on. As you can see here on the slide, on the diagram, like adding, like introducing like these optimization techniques actually affects retrieval quality, and the last column is actually where we kind of enable again OS sampling, and you can see how it jumps back again to 99%. So the retrieval quality drop is kind of minimal and almost negligible in this case. Okay, I hope this was clear. Now, even with all these retrieval techniques that we covered, that we talked about with hybrid search, semantic re-ranking, query rewriting, like all working together in order to improve retrieval quality, we can see that traditional RAG can still struggle in certain scenarios, and that is, primarily when dealing with complex questions, complex queries, such as the ones that you see on the slide, like multi-part questions, chain questions, and so on. Typically, queries and questions that cannot be answered in a single retrieval step. These types of questions typically require combining multiple pieces of information, often spread across different sources, different documents, and sometimes it even requires refining the search based on the intermediate search results, or actually based on what we learned along the way, which brings us to our next and final topic for today, and that is agentic RAG, which introduces a more dynamic and iterative approach to retrieval. Now, before we dive into Azure AI Search and how we can do this within Azure AI Search, it helps to first kind of clarify what we even mean by agentic RAG. So when talking about AI agents, there is one idea or one concept that often comes up, and that is reasoning. And we typically define reasoning as a ability to kind of analyze and understand current situation, to determine what to do next, which action to take, and so on. So in the context of RAG, of retrieval, right? In the context of RAG, we can think of an agent as as a layer on top of the retrieval pipeline that can analyze, that can understand when the answer is maybe incorrect or low quality, can determine when or which additional information might be needed, can decide which action to take in order to improve the answer, which is typically another round of retrieval, knowledge retrieval, right? But using a refined search query, and can also run this in a loop until the answer is good enough. So the example on the slide that you see on the slide illustrates one possible implementation of agentic RAG. Again, it's just a concept. There is no one single way to implement it, but this illustrates one potential implementation where we use evaluation and reflection steps to guide subsequent retrieval iterations. So in this example, instead of immediately showing answer after it's generated by an LLM, we can actually evaluate that answer to understand whether that answer may be, there are different types of evaluations, but just some examples. We can evaluate whether the retrieved context is even relevant to the user query. We can evaluate whether the generated answer is grounded in that retrieved context, and so on. And then based on that evaluation, we can then reflect. Again, when we say we can use language model for these operations, maybe another language model or something like that. We can reflect on that answer to kind of identify what might be missing, and then based on that reflection information, based on that, we can actually generate a refined query and then perform another round of knowledge retrieval and generation, and then we can run this in a loop, right? And until the answer is kind of good enough. So this iterative approach is what enables agentic RAG to better handle those complex queries compared to a linear RAG pipeline. Now, as I already mentioned before, Azure AI Search has its own take on this, on agentic RAG, its own implementation. It's not exactly the same as the one we mentioned, we showcased here. This is a typical, what we would typically kind of have. In Azure AI Search, it's a little bit more, it's a little bit different, but it follows the same principles. It's the same concept under the hood. Agentic, it's called agentic RAG, is in Azure AI Search, is implemented under the name agentic retrieval. And it's Azure's native approach to agentic RAG, let's put it that way. At a high level, we can define it as a, let's say, a planned multi-step retrieval workflow. But I'm going to explain now how it actually works. So it all starts with our application sending a user query, like search request, right, to Azure AI Search, passing in user input, user query, and also conversation history. And this is one of the main differences compared to traditional search, because traditional search works only on a single query, while agentic retrieval can actually accept conversation history and can then use that conversational history to better understand the user intent. So it kind of even makes that, if you remember from the beginning, I mentioned that we typically have that query rewriting step that aims to capture that conversational context. So when agentic retrieval kind of almost makes that step obsolete or unnecessary, like having it like a separate pre-processing step outside of Azure AI Search, because it can now accept conversation history and understand that context itself. So the next step, or let's say the first step after the query is received, is called query planning. This is where Azure AI Search actually sends that user input together with the conversation history to language model. And this is where that agentic aspect comes into play, because the model analyzes the user input, the conversation history, to better understand the underlying information need. And then instead of issuing a single broad, let's say, search query, the LLM can actually break complex or compound questions into multiple focused subqueries, as you can see here on the diagram. Now, all those subqueries are then executed against the underlying knowledge sources. Knowledge sources can be different, but the most typical one is search index. I will explain that in a minute. I will showcase it through the Azure portal. So we generate multiple subqueries, and then all those subqueries are executed in parallel using the exact same retrieval stack we discussed earlier, if we are using search index as the underlying knowledge source. So L1 recall followed by L2 semantic re-ranking in this case. And semantic re-ranking is actually mandatory with agentic retrieval, maybe worth mentioning. And then depending on our settings, after all these subqueries are executed, depending on our settings, the system, Azure AI Search, may return either the verbatim content that it retrieved from these knowledge sources, so the source content, which we can then use as a grounding context when calling LLM. But what's interesting, it can actually also call LLM itself to generate the answer using answer synthesis feature, to generate the answer kind of from that retrieved information. So we have two options. We can either get verbatim content from the knowledge sources or an LLM generated answer. Plus, we also get references, which we can then use to, for citations. We get the activity log, which can be used for debugging to understand what actually happened under the hood. We can see all the subqueries that were executed against, which underlying knowledge source, how many tokens each subquery spent, and so on. Okay, I'm going to switch now to Azure portal again. So just give me a moment to switch screen sharing, just to showcase how this looks like in practice. Just a second. Okay, here it is. hope you can see it. So I mentioned two new concepts. Those were like the knowledge base and the knowledge source. Knowledge base and knowledge source are actually core building blocks of agentic retrieval in Azure AI Search. Knowledge base is, we can call it the main orchestrator of agentic retrieval. It accepts the user, like our search request, the user query. It calls LLM, to perform query planning. Then it executes all those subqueries against the underlying knowledge sources. It then calls LLM to generate an answer and so on. So it really orchestrates the whole process, and you can almost think of it as a kind of knowledge agent. Technically, I think that would be a good name. So it's not just a knowledge base because it really has some behavior to it. It's not just kind of that it keeps the knowledge, right? It actually orchestrates this whole process. So let me start here. I'm going to create one new knowledge base. This is actually this will be relatively quick, so we can go through the whole process. I'm going to create a new knowledge base. We need to give it a name, and then from here we can actually reference one or more knowledge sources. Now, don't confuse knowledge source with the data source. We still have the data source as part of the data ingestion pipeline from the beginning, if you remember. So they are not the same thing. Data source provides the raw data, let's say documents in our case, while the knowledge source simply encapsulates the source of retrievable knowledge. So knowledge that is already prepared for retrieval, for example, search index, right? Search index contains the retrievable knowledge in our case. However, it can also represent a direct connection, as you can see here on the screen. It can also represent a direct connection to some external system, such as, for example, Bing, which enables web search. For example, SharePoint, which enables direct queries against SharePoint, which means SharePoint documents, which means that we don't have to necessarily index SharePoint documents into the Azure AI Search, and so on. So there are different underlying like data sources. In our case, we are now going to use search index because we already have it, right? We'll use existing one. So let me select the existing search index. As you can see here, we also have some additional metadata, such as, for example, knowledge source description. This metadata is passed to LLM during query planning, so it can actually help kind of guide the model, the language model during query planning and knowledge source selection. So I'm going to create this one. So we have the knowledge base, right? We still didn't create it fully. We have the knowledge source attached to the knowledge base. The next thing is to kind of select the LLM. So we already mentioned this query planning and answer synthesis capability. So in order to enable that, we need to connect our knowledge base to a language model. In this case, I'm going to select a model deployment that was already created from Microsoft Foundry. We are going to use GPT-5 Mini. I'm going to just save this. This is just basically now, we simply defined an LLM that is going to be used for query planning and answer synthesis. Obviously, the model can impact the quality of those operations, but our demo is quite simple, so GPT-5 Mini is probably good enough. Now, besides these, there are a couple of additional like configuration options and settings that are worth mentioning, such as, for example, retrieval instructions. Similarly to knowledge source description, retrieval instructions are also passed as part of the prompt, to LLM, and it also can help guide the model during query planning and knowledge source selection. Retrieval instructions are especially important if you have multiple knowledge sources, right? So you can actually provide some instructions to LLM when to pick which knowledge source and when to execute which query, against which knowledge source, like what type of information can each knowledge source provide. In our case, we only have one knowledge source as a simple demo, so no need to kind of enter anything here. Another important setting is the output mode. I already mentioned that the Azure AI Search in this case can actually return the verbatim content, the source content from the underlying knowledge sources. So in this case, the result is very similar to what we would get using a traditional search. obviously, under the hood, it's still different because we still have that query planning and multiple subqueries executed and so on. But the final result format is kind of similar. We just get the list of the potential results, maybe relevant information. We still need to then, after that, call LLM passing this as a context, as a grounding context. Or we can select answer synthesis, in which case the Azure AI Search will actually call and use LLM, provide that information, and we would get just an LLM generated answer. So it kind of handles that step for us. And technically, we get the RAG built into the Azure AI Search. If we enable answer synthesis, we also have answer instructions similar to retrieval instructions. This is also passed as part of the prompt to LLM. It helps guide the model, during answer generation. Like we can provide some instructions, like how we want, I don't know, for example, we want very concise, concrete answers and so on. This is where we would put those instructions. So we now have everything that is needed. We can simply now create the knowledge base, and that's it. You can see that we have like a really interesting, nice test UI inside Azure AI Search. So we can immediately test how our agent works with all these knowledge sources, instructions, and everything that we put here. And I'm going to use the same query that we actually used before when we were testing our retrieval, if you remember, like when we were testing if we can retrieve this information, if it was kind of extracted and ingested properly. We are going to actually ask that question now. So since we have the answer synthesis enabled, right, that means that we are going to get the LLM generated answer. And as you can see, the agent was able to actually answer correctly. Again, it's not like that complex example, but it showcases what I was talking about earlier, that it's actually important to kind of preserve the structure of the document whenever possible, because it helps agent understand the content better, right? If this whole text was just presented as a flat text, there would be a high chance that the model would actually confuse these numbers and information, right? So it might actually return a wrong one. In this case, it was able to answer correctly. As you can see, amply +2 or more costs $89, and that's basically this one. Now, in addition to that, we also get like the citations, the sources. We can also open this debug window. This is our activity log that I mentioned earlier, so we can actually see which subqueries were executed, against which knowledge base, knowledge sources, how many tokens each subquery consumed, and so on. So it's kind of a helpful tool for debugging. And there is one more setting that I forgot to mention. It's actually quite important, and that is reasoning effort. Reasoning effort actually determines the level of LLM involvement or LLM processing during query planning and answer synthesis. It has 3 values, like minimal, low, and medium. Minimal means that there is no query planning, there is no answer synthesis, right? In this case, knowledge base simply acts as a fan-out mechanism. It simply forwards your input, your query, to all underlying knowledge sources. So you might be thinking, why do we even need it, right? In that case, there is no agentic retrieval. It simply forwards our query to all the underlying knowledge sources. But it can act, it can be helpful. It acts as a simple fan-out mechanism. And there is one more benefit that I also forgot to mention, and that is that knowledge base actually comes with built-in MCP. So even if you are using minimal reasoning effort, you don't want to use agentic retrieval, you can still kind of benefit by getting an MCP endpoint for free, which makes it really easy to integrate with other agents, for example. The second level is low. Low enables a single round of knowledge retrieval and generation of query planning, essentially, but only single round. And then we have medium, which enables a follow-up retrieval and generation round. So the agent will first retrieve. It first goes through one pass of query planning and answer generation. Then the answer gets evaluated. If it's not good, and if it's determined that it's not good enough, there is like a follow-up retrieval and generation round. But unfortunately, only one round. It cannot like loop indefinitely. But as you can see here, like we have minimal, low, and medium. So the naming kind of suggests that there might be another setting that's called maybe high or something. Right now, the agentic retrieval is in preview. Most of these actually agentic retrieval features are in preview, so there is no like related SLA. So maybe when it goes, to being generally available, maybe there will be more like additional settings here that would enable that iterative approach. We kind of have it with medium, but it's only one additional iteration enabled. Okay, that was it for me. I hope this was useful. I'm going to switch over back to the presentation. I just want to say that what we talked about, like in like this whole Azure AI Search retrieval stack, is kind of pick and choose, right? Like we covered a lot of things, like from data ingestion pipeline, retrieval pipeline with different retrieval techniques, text search, vector search, hybrid search, semantic re-ranking, query rewriting, then agentic retrieval, and so on. But as I mentioned, it's kind of pick and choose. You can kind of opt out of some of these things. For example, you can decide, you can implement your own data ingestion pipeline completely outside of Azure AI Search for whatever reason, if the built-in features are not kind of sufficient for your use case. And then even if you implement a custom data ingestion pipeline, you can still use the whole retrieval pipeline. Or you can, use agentic retrieval, or you can decide not to even use agentic retrieval because maybe it doesn't match your needs, and then you implement your own agentic reg on top of those traditional search APIs. So it's kind of up to you and up to your use case. Thank you very much for joining us today. I hope this was interesting and useful. If you have any questions, now is the time to ask. There is one question from Dina. How do we ensure that the agent doesn't return documents or answers that the user shouldn't have access to? For example, if financial documents are indexed alongside general company policies, how does Azure AI Search prevent data leakage across user roles? Okay, we didn't have a chance to talk about security. This was a little bit longer session, so we had to cut something. So thank you for the question. The core security mechanism in general in reg applications, but in this case as well, is actually relatively straightforward. It's kind of a combination of permission metadata stored in documents as part of our index, and combined with filtering at query time. So during indexing, we can actually take our access control information, whatever that is. It might be user IDs, maybe group memberships, sensitivity labels, and so on. We take that access control information and we write them as metadata. We store them as metadata alongside our document content. And then at query time, the caller's identity is checked against that metadata. So any documents that the user is not authorized to see are then excluded before results ever reach LLM. So unauthorized content kind of never enters the context window, right? Because we do it it's enforced at the retrieval layer, we can say. So the concept is quite simple, but there are many different ways to implement it, right? The main thing is that, okay, we need to store some security information as part of the metadata, and then we filter it at query time. We can do it completely manually, for example, where we simply push access control information, maybe role names, permission names, whatever, into index fields like as metadata, and then at query time we can filter it using a simple string match. So very simple approach, and it obviously works with any identity system because in that case you're doing everything yourself manually. However, one good thing to mention is that Azure AI Search also provides built-in integrations that automate, some of this stuff obviously for Microsoft data sources. For example, it can automatically pull access control information from SharePoint, Azure Data Lake storage. It can also carry over the sensitivity labels from Microsoft Purview and so on. So in the end, the pattern is the same, right? If you're doing it manually or using some of these, built-in integrations, we need the metadata in our index, and then we filter it. We filter it at query time. These integrations in Azure AI Search kind of just make it easier to, let's say, operationalize at scale. Okay. I don't see any additional questions. So if there is nothing else, we can call it a day, I guess. Thank you very much for being with us today.